A quick update to the quick reference card that I've been building. I fixed a couple errors and added a couple things, and I'm just going to walk you through it real quickly. I had a bug here. This was actually an equals. I've added an arrow there. There was a couple little things about the way that the system instructions were done that have now been fixed. This one here was program counter gets program counter, or this was PC++. Now it's made a little bit more clear that the difference between jump and link is the base register. In jump and link, it's PC gets PC plus immediate. In jump and link register, it's PC gets RS1 plus immediate. But the structure of the return address storing is the same. The big change, though, that I made is I added a bit more information and shifted a few things around the control status registers. I didn't talk too much about those in the video on the secondary instructions, the system call and stuff like that. But one of the instructions in the system call, CSR-RW, is actually a suite of instructions that allows you to write control status registers to a register file, read from it back and forth, set or clear bits based on that. And I wanted to do a bit more on what those control status registers are and how they work. There are a number of, there are 3 hex digits worth of, so 12 bits worth of control status register space that can be allocated. There are a set of about a dozen that are standard for RISC-V that are always implemented, and then other implementations have more. The basic ones, I had a few that were missing, so I added them all in, and then I also added some timers. So the basic ones are machine status, and then this one, MISA, is the Machine Instruction Set Architecture or extensions. This is how you tell the machine what it is. Is it RISC-16? Is it RISC-32? RISC-64? Which extensions are implemented by the hardware, like the floating point extension or the multiply divide extension. This register will tell you what those are. Then you have a register that enables interrupts, a register that gives you the trap vector address table, so where you're going to look for trap processing handling routines or the addresses there too. This is a scratch register that trap handlers can use for temporary storage so that they don't collide with any of the standard registers when you're doing trap execution. Then you have a register that says what caused the trap and a register that says what type of trap it is, whether it's an exception or an interrupt or something else. And then you have a register that says interrupt pending. Is there an interrupt that is waiting to be handled? That register and flags within that register will tell you whether you have failed to handle an interrupt as it's pending. So those are the status registers that are required to be implemented, and then there's a bunch of others that can be done. The other thing that is required to be implemented are timers. So we have cycle or cycle H, cycle and cycle H. Cycle is at C00, cycle H is at C80. This is the number of cycles since the machine was turned on. Time and time H are at C01 and C81. This is the number of clock ticks that have elapsed since the machine was turned on. And that's not like seconds. That depends on the resonant frequency of the internal timer, which is sometimes 10 megahertz, sometimes 37 point whatever, based on a quartz crystal, that kind of a thing. And then this is the number of instructions that have been retired since turn on. That can be an indication of what you've got done, how many instructions have been retired or completed. These are all 64-bit counters, even though we're only implementing RISC-V 32, because a 32-bit counter you can't do much with. And so these are implemented as 2 32-bit registers, with the low one at 00 and the high one at 80, or 0181, 0282. So they come in these pairs. And then the privilege modes are the same, but I've shifted them around. Later on, I'm going to spend a bit of time revamping this, because I think it's not as clear as it could be. It's really compact, and it just gives you a hint at what kind of things are available. And I would encourage people who want to use the float extensions to go and look at that documentation. Same with the multiply divide extensions. The goal here is just to say these exist and you can play with them. But I think there's a little bit of room to make this a bit more useful rather than just an indication of what you might do. So in addition to a few little bugs and things that I fixed, the last one, when we were talking about load and store, I had a question about whether this AIUPC LW was in fact the correct pseudo instruction expansion for a far load or a far store. There's a few ways you can do it. A near load or store, you have a base register, and then if the immediate is, plus or minus 2 to the, 2 to the 12, plus or minus sort of 12, plus or minus 2,000-ish bytes away from the base register that you're using, this works fine. If you're farther than that, there's actually two ways you can do it. One is to use the load address pseudo instruction to put an address in R1 instead of to put the address you want to access in R1. And that is over here. I've added this, spaced this out a little bit further in the pseudo instructions. And load address is actually implemented as relative to the program counter. There's a couple of ways to do it. You can just load a value, like in load immediate, you can load a value and then add to it. You can do that with load upper immediate and then add immediate. A small load immediate can just be done with add immediate, but a larger load immediate is done with load upper immediate. The question is, why are we using this AIUPC, add upper immediate PC, instead of add upper immediate or load upper immediate by itself? And the reason is that the load addresses, when you're constructing the addresses, doing them relative to the program counter allows the assembler to actually construct that in a more reliable way. And so that's why this stuff here, AIUPC into the destination register, and then this is an assembler shortcut for the high 20 bits of the symbol that you're accessing, and then the low 12 bits of the symbol that you're accessing is then added using load word. So instead of just constructing the address and putting it into RS1, that's what LA would do, you can do this with two instructions instead of 3, right? You can construct the top of the address using AIUPC, and then you can just use that with an immediate offset to the bottom address, since the immediate offsets are 12 bits. So this is 2 instructions to do a far load. Or if you use LA for load address, you would do it in 3 instructions. You would create the address using this process, and then you would use load with RS as that address. So this stuff is a little bit messy, and I wanted to sort of clarify it a little bit. If this is still a little confusing, let me know, and I can look at some other ways of doing this or breaking out these pseudo instructions. If you play around with the float instructions and you find some better way to do this, then I'm happy to entertain different ways of sort of expanding that until we get the more or less standard sheet that we're looking for. So that's just a quick update.